Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss finding and analyzing polynomial and exponential growth and decay. So in this topic, we will consider how we need to analyze and find the polynomial growth of data. That is, when we are looking at data, how do we determine if it is growing according to n to the b, and how do we find that unknown b? And we're going to walk through an example of this. We will also consider how we need to analyze and find exponential growth or decay of data, where it is now of the form a times e to the bn, where n is the independent variable in time, usually. And again, we will walk through an example. Now, from our discussions, we've already seen that we can fit a polynomial to data. So, for example, given this data, we can find a least squares best fitting line that passes through this data. Alternatively, we can also find a least squares best fitting quadratic that passes through this data. You may also recall that we can fit any linear combination of functions of an independent variable to data. So in this case, we may look at this data and suspect it is of the form some constant plus b times the logarithm of n. So in other words, it's a times the function 1 plus b times the function ln of n. So to find the best fitting polynomial, well, we're just going to have the function 1 evaluate at each of the n values, which is of course 1, and then we evaluate the logarithm at each of the n values. Having done this, we then have the target vector t, and then we simply solve this system of linear equations. A is associated with a constant 1, b is the multiplier of the logarithm function. Solving this system gives us a and b, and that would give us the best fitting function of the form a plus b times log of n. Now instead, let's consider these situations. You've implemented an algorithm, and your runtime shows polynomial growth with respect to the capacity n. So t of n is a times n to the b for some power b plus lower order terms. Alternatively, let's say you're looking at nature, and you are looking at a phenomena that appears to give exponential growth or decay. Consequently, the size or quantity is equal to some constant times e to the bt, where this is the exponential growth. Notice that neither of these functions on the right-hand side is of the form of a polynomial. It is a times n to the b, where both a and b may be unknown, or a times e to the bt, where again the coefficient a and the power b are unknown. However, if you look at the first case and write it in the form y is equal to a times x to the b, then note that log of y is equal to log of a times x to the b. But by the properties of the logarithm of a times x to the b is equal to ln of a plus b times ln of x. In the second case, if we have it in the form y is equal to a times e to the b times x, then taking the logarithm of both sides, we have that y, the logarithm of y, is equal to the logarithm of a plus b times x. Well, this is now nice because both of these are in the form an unknown plus an unknown times a function of x. In the second case, it's a polynomial. Now, the term polynomial growth is used to describe any function that grows according to big O of n to the d, where d is some real number. And it doesn't have to be an integer. So normally we think of polynomials as simply having powers that are integers, but we'll be quite happy to say that n to the 1.3 would demonstrate polynomial growth. So, for example, suppose that you've just implemented a biparental heap that contains n items. Well, looking at the structure of the algorithms for a biparental heap, you are aware that certain operations are big O of the square root of n. Alternatively, suppose you've just authored Karatsuba's algorithm for multiplying two n-digit integers. You may be aware that the runtime of this algorithm should be big O of n to the log base 2 of 3. So in the first example, we have n to the 0.5. In the second case, we have n to the 1.585, at least approximately. So both of these implementations should demonstrate polynomial growth in runtime with respect to the problem size. All right, so let's suppose that we've implemented that biparental heap, and then we fill that heap with n equaling 2 to the k items for various values of k. We then run the operations and time the operations. We then plot the number n versus the runtime. Now, we know from our analysis of the biparental heap that the runtime should be big O square root of n. But looking at this data, does this represent big O square root of n, or is it big O of n to the 2/3, that is n to the 0.666? The problem is we can always fit something of the form c times the square root of n to this data and get the unknown c, but is that actually the best fitting function? What we'd actually like to do is find the best fitting function of the form a times n to the b and then c if the unknown b is at least close to 0.5. Alternatively, suppose that you've incorporated Karatsuba's algorithm in some large integer class, and you then test the runtime of your integer multiplication algorithms. So for example, you are multiplying two n-digit integers where n is perhaps 64 or 128, and you time this. Now, you plot the data. Well, this data may be of the form n to the log base 2 of 3, but perhaps it's order n squared. Recall that by default, multiplying two digits using the algorithms you saw in secondary school, those algorithms are order n squared. Karatsuba's algorithm, if implemented correctly, is big O of n to the log base 2 of 3. So, does this image demonstrate polynomial growth or quadratic growth, or is it order n to the log base 2 of 3. What we'd really like to do is find the best fitting function of the form a times n to the b, and then see if b is at least approximately equal to 1.585 and not equal to 2. Alternatively, suppose you've implemented a new algorithm and you'd like to determine the asymptotic behavior of your algorithm. So, for example, you may be implementing a heap, but a heap that is dynamically modifiable. So you'd like to determine what is the runtime of your data structure. So once again, you'd like to fit a function of the form a times n to the b, and then see what the power b is, or at least approximately is. The problem here, however, is a times n to the b is not of the form a times one function plus b times a different function. The unknowns a and b must both be found, and we cannot do it with linear regression as we have seen so far. Suppose our runtimes, or more generally our data, is demonstrating polynomial growth, so therefore t of n is some unknown a times n to the b plus lower order terms, again where b may be unknown. Therefore, if we have a large specific value of n, say n sub k, then the runtime is going for that n sub k is some value t sub k, and that's going to be approximately a times n sub k raised to the power b. Okay, so taking the logarithm of both sides, the logarithm of the runtime is equal to the logarithm of a times n sub k raised to the power b. Now you know that ln of xy is equal to ln of x plus ln of y, and we can expand that there, and you know that ln of x to the y is just y times ln of x, and we can therefore simplify the right hand side. Now ln of a is unknown, therefore ln of a is an unknown constant. B is an unknown constant, and we have ln of n sub k. So we have an unknown constant times 1 plus an unknown constant times ln of n. That sounds like we have a linear combination of given functions. All right, let's try this out. Here are some n values, and I've spaced them out exponentially, so powers of 2, but this isn't required. Now, I'm going to create a vector of t values, and each t value will be the corresponding n value raised to the power 1.35 and all multiplied by 5.32. All right, so this is the relationship between n and t. So we can plot the n values versus the t values, and you can see that the t values are increasing polynomially in something that looks like it is superlinear and probably not quadratic. However, if we now plot the natural logarithm of the n values versus the natural logarithm of the corresponding t values, we see that these fall on a straight line, and we can find the equation of that line. The slope of this line is 1.35, and the y-intercept is the natural logarithm of 5.32. Again, it's important to remember that the natural logarithm is implemented in C++, MATLAB, and most other programming languages as log of x. If you wanted log base 2 of x, you could either use a formula, or there's often a log2 function, and if you wanted the common logarithm, you would use a function usually named log10. All right, how are we going to use this? Well, suppose you've authored an algorithm and you've run it on various input sizes, that is, different values of n, and you've recorded the runtime. Now there's two issues here. First, your program is not going to be running in exactly a times n to the b time. Instead, it's going to be running in a times n to the b plus lower order terms. Consequently, a log-log plot will never be exactly a straight line. Also, of course, there's going to be errors or noise in your timings. So any points that you find will not fall on a straight line. All right, so the first step we're going to do is collect the data. So what we're going to do is we're going to use exponentially growing values of n. So n is going to be equal to 2 to the k for k going from 0 to some n max. And what we'll do then is record the time it takes your algorithm to run for each value of n equaling 2 to the k. We'll store this in a variable called t sub k. Now, we want to get as many points as is reasonable, so you should try to get at least up to sizes of 2 to the 16. So essentially, n max should be somewhere around, if not greater than, 16. What this does is this ensures that any lower order terms are going to be swamped out by the dominant term of the runtime. So therefore, there's not going to be noise introduced from those lower order terms. They are relatively insignificant. Now, if having such a large value of n max produces a problem size that's too large to deal with, so if n being 2 to the 16 is simply too large, you can use values of n that are powers of square root of 2 to the power k, or even the cube root of 2 to the power k. The reason we're using square root or cube root of powers of k is that at least every second or third value will be a power of 2. Recall that the brackets around those two are the floor function, so the integer less than or equal to that particular value, whatever it calculates out to. Another thing that's useful is don't just have one sample per value of n. Instead, we'd like to have multiple samples. So for example, if we had 3 samples at n sub k, we will call those 3 samples t sub k1, t sub k2, and t sub k3. Now, the reason for taking multiple samples is you cannot determine an error from a single sample. For example, let's assume that we have analyzed our Gaussian elimination implementation and we have determined that the runtime should be based on this number of instructions being executed. So proportional to this. You're wondering why there is an n ln n in that expression? Well, that's because when we are finding the pivot element, assuming random distribution, we will only be occasionally updating where the largest entry is. So that's where that comes from. But the dominant term is, of course, n cubed. Now, if n is equal to 10, then the higher order term is just twice that of the lower order terms. If n is equal to 100, then the higher order term is 23.5 times the lower order terms. So essentially, the lower order terms contribute only a 4% relative error. As we go on higher and higher, the higher order term will be 0.24 times n times the lower order terms. So the lower order terms become insignificant. Let's see how we will therefore use this. So for example, suppose we've implemented our algorithm and now we run that program and time it. Timing it, we have different values of n, be that the number of objects in the container being analyzed, or be it the number of digits in integers being multiplied, or be it the size of a matrix and or vector. So for each value of n, notice that they are exponentially increasing. We have taken 3 samples with respect to the runtime. Now, this is growing. It could be quadratic, or it's definitely superlinear. So it's little omega of n, but it doesn't look quadratic. So what is the growth? Well, that's what we'd like to determine. We don't know what the growth is. We can trivially fit a quadratic curve to this, but the significance of that fit is useless if the data is not actually quadratic. The next step is the analysis. So what we will do is we will do a log-log plot of n versus t. So that is, we take the logarithms of each of the n values and we take the logarithm of each of the runtimes. Now, it doesn't matter what the base of the logarithm is, so long as you use the same base for both n and t. We're going to be using a base 2 logarithm because we have explicitly chosen the values of n to be powers of 2. Now, just a reminder, log base 2 of n is very often written in the literature as lg of n. Now, what we will then do is we will determine whether or not, as n gets larger, if this plot becomes a straight line. If it actually isn't a straight line, then we may not have polynomial growth. We may actually have exponential growth, either exponential growth or exponential decay. Also, what we're going to do is we're going to look at the plot, and if it is linear or appears to be approaching something that is linear, then we will determine at which point the lower order terms have negligible impact. For example, here we see a log-log plot of the previous data. Now, notice that at some point around after this value here, the points seem to be falling on a straight line. Consequently, we're going to discard all values less than capital N sub min. So we will only be interested in the points from n sub min to n sub max. We're going to be doing this visually. Then notice that these points do appear to be falling on a straight line, and therefore we can do the next step, and that's find a least squares best fitting polynomial. Specifically, a least squares best fitting straight line. So we're going to do that linear regression. On the points that we determined were reasonable, that is where they appear to be a straight line, we will perform a linear regression. So we are going to be going for values of n between 2 to the capital N sub min all the way up to 2 to the capital N sub max. Now, the two functions that we have, here's the van der Moon matrix, are b times log base 2 of n plus a times 1. Well, log base 2 of 2 to some variable is just that variable. So remember that we have 3 data points per value of n. Therefore, we're going to have 3 values of n sub min, then 3 values of n sub min plus 1, because we have 2 to the n sub min plus 1, and so on and so forth. And then finally 3 values of n sub max. The vector of values on the right-hand side are the logarithms of base 2 of the times taken at n sub min. There's 3 of them. Then the times at n sub min plus 1, and so on and so forth up until the last point. So once again, we have 3 values for each value of n, and we have 3 values of n in the left-hand matrix. We will then solve this system for both b and a. So for example, given this restricted range, we find the least squares best fitting line, and it appears to be approximately 1.572 times the value of n, which is log base 2 of n, minus 4.325. All right, now there is the original data below, and we found that log of t is approximately 1.572 times log of n minus 4.325. So therefore it follows that 2 to the log base 2 of t, which is just t, is therefore 2 to that linear polynomial. Now, you know from secondary school that 2 to the xy is just 2 to the x times 2 to the y. Now, also, we can just evaluate the second term, but the first term in that product, recall that beta raised to the power a times log base beta of n is just n to the a, and you can just use your rules of the logarithm and exponents from secondary school to determine that that is actually true. Consequently, this expression simplifies to this expression here. All right, so consequently, we can just rewrite that as follows, and we can make a plot of that curve through that data. Now, remember, this data has noise in it. Let us assume that we were implementing and timing the Karatsuba integer multiplication algorithm, which has a runtime of n to the log base 2 of 3 time, which is approximately n to the 1.585 time. Assuming we have not created a more optimal implementation, it seems reasonable that the difference in the exponent is simply the result of the noise in our data. And therefore it is reasonable to assume that our implementation of the algorithm is indeed likely correct. So we did not accidentally, for example, implement an algorithm that was still order n squared. All right, so we have gone through one example of how we could find the asymptotic growth of data given one particular example. And this applies to any other data that is polynomially growing. And this is in general what engineers end up using. However, we will also look at one more case. That is when the data is exponentially growing. In contrast to polynomial growth, it's also possible that natural phenomena may obey approximately either exponential growth or decay, and this is described by any function that is big theta of e to the bn, where b is some non-zero real value and n is usually in terms of time. So, for example, this may include radioactive decay. This is the expression that gives the amount of carbon-14 that remains after n years. So at time t equals 0 years, there is m naught carbon-14. If you want to know how much carbon-14 will be there after 1,000 years, you plug in n is equal to 1,000 and you calculate the result. You can also, from this, determine the half-life of carbon-14, which is 5,730 years. Plus or minus 40 years, that's the error, but still in that range. Meaning that after that period of time, if you started with 1 kilogram of pure carbon-14, after those 5, almost 6 millennia, then only half of that carbon-14 would remain. Now, that's radioactive decay or exponential decay. However, exponential growth, of course, also describes exponential growth. Now, Moore's law says that the number of transistors in a dense integrated circle doubles at the rate of every 2 years, starting with around 1970. What that says is there is some constant C such that the number of transistors in that dense circuit can be determined by plugging in the year n since 1970 into this formula. Now, I was going to describe the exponential growth of an invasive species. However, this is much more interesting. I found this very fascinating paper by Riccardi and Ryan, which was the exponential growth of invasive species denialism. These are papers published that deny the issues that invasive species pose on the environment they are invading. We know that invasive species are very dangerous. However, the number of papers being written against this view has actually been shown by Anthony and Rachel that it is growing exponentially since 1990. And you can find approximately the number of papers written any year by plugging in the number of years since 1990 into this expression, and it's actually an amazingly close fit. Now, there is scientific skepticism, but scientific skepticism is the refusal to accept a proposition until there is sufficient evidence to support that proposition. That is reasonable scientific skepticism. And that evidence must, of course, be replicable. Denialism, on the other hand, is denying a proposition or even a scientific theory despite significant and verified evidence supporting that proposition, theory, or hypothesis. And again, this is for this papers, the number of papers since 1990. So if you wanted to find the present time, you might plug in around 30 years or 30 into that equation. Now, fortunately, this isn't happening yet, but suppose that each year you and a bunch of your colleagues were going out and counting the number of hives found on the Asian giant hornet in North America. Every year you observe and you count, and you notice that over time the growth appears to be exponentially increasing. Basically, what this says is the count of the number of hives is something of the form a times e to the bn, where n is the number of years since your initial counting. So suppose that data does have exponential or growth or decay. Consequently, the count, be it a measure of mass, be it a counting of number of objects, there's going to be a relationship of the form the count at time n is equal to a times e to the bn, where a and b are real numbers. B is non-zero, otherwise we have a constant function. Consequently, if we were to have a given value of n, say n sub k, then the count at time n sub k is going to be some value c sub k equaling approximately, usually, a times e to the b n sub k. All right, so suppose that we have the count at some time at time n sub k, and that count is c sub k. Well, if we're taking the logarithm of both sides, then the logarithm of the left-hand side, the logarithm of the count, is equal to the logarithm of a e to the b n sub k. You know, however, that the logarithm of a product is the product of the logarithms, is the sum of the logarithms. I'm sorry. All right, so that's that expression there. And the logarithm of an exponential is simply the power. All right, so now the logarithm of the count is equal to a constant plus a second constant times n. This is a linear expression, or a linear polynomial in n. Nice. Let's try this out. I'm going to create 11 equally spaced points from 0 to 10. I will then evaluate these 10 points at the function 8.23 times e to the negative 0.2 times n. So each value of the count is exactly given by this formula. We can plot the n values versus the c values, or the counts or quantities, and we see that they do indeed appear to be exponentially decreasing or exponentially decaying. And there is a reasonable match of a curve passing through those points. It does appear that they are tending towards 0. If, however, we plot the n values versus the natural logarithm of the c values, we get a different plot. Notice that this is a straight line. We can find the equation of that line, and we note that the slope of this line is negative 0.2. Also, the y-intercept is the natural logarithm of 8.23. All right, so how can we use this? You've been collecting your data, so at various times you've been counting or measuring some quantity, and you understand that the quantity is growing or decaying exponentially. There are, however, two issues. First, there's going to be noise in your data. So the count's not going to be perfect. You may miss some information, or you may accidentally count too much. Also, there may be other factors involved. Hopefully, these other factors are significantly less than the exponential growth or decay. So the first step is to collect data. So for different values of time, n sub naught, n sub 1, n sub 2, all the way up to n sub capital N, what we're going to do is calculate our count. Okay, so for each of these times, we've counted or measured some quantity, and it is changing. Now, try to get as many points as is reasonable. Also, we often do have equally spaced points in time. For example, we may be taking a sample once a year, or once a month, or once a day. But this is not necessarily required. And if we miss a particular day, month, or year, it's not the end of the world. We just discard that or do not have that datum. Often, the first value is when we consider time t naught, but that's also not required. Now, as before, it's actually better to have at least 2 samples per n, as if you have just a single value, you have no idea as to what the error is. So we may actually have 3 samples with each n sub k value. So we'll represent these 3 samples by c sub k1, c sub k2, and c sub k3. And again, with 3 values, you can actually get a good estimate as to what the error of your reading is. This is not possible with a single sample. Okay, so let's say that this is the data we've collected. And here we have integer values of n, and at every integer time we are measuring some value, in this case 3 times, and then we plot it. And it does look like it is exponentially decaying. All right, so we have something that appears to be exponentially decaying. Hopefully, it may actually be decaying 1 over n, which is n to the negative 1, but we're going to be able to determine, is this indeed exponential decay in our analysis? So what we will do is we'll have a log plot of the n sub k values versus the logarithms of the counts at that time. Now, it doesn't matter what the base of the logarithm is. Could be the natural logarithm, could be log base 2. It doesn't matter. But if you choose anything other than the natural logarithm, just be sure to use that same base later when you raise the result to the exponent of that base. At this point, you're going to look at the data and determine whether or not it appears to be in approximately a straight line. If it isn't, you may actually have polynomial growth or decay, or you may have hyper-exponential growth or decay. All right, we've taken the logarithm of all the previous values and we've plotted them. Well, now these points do seem to fall in approximately a straight line. So this suggests that this data is indeed exponential. Next step, linear regression. So on the points that we have found, we perform a linear regression to find the least squares best fitting straight line. So here is our Vandermonde matrix. Now you'll recall that we are matching a polynomial of the form a plus b times n, except we have 3 readings, at least in this example, per value of n, and so consequently we would have capital N plus 1 all times 3 different values. So it's a times 1 plus b times n, and we have each n value replicated 3 times. We also take the logarithms of each of the counts at these points. We then solve the linear regression problem to find the coefficients a and b. So, for example, suppose that in the previous example we did the linear regression and we found that this data was of the form 1.572 minus 0.235n. So that is the equation of this line that is the best fitting line to this data. Thus, if the natural logarithm of the count or quantity at time n is approximately equal to 1.572 minus 0.235n, it therefore follows that the count or quantity is equal to e raised to the logarithm of the count. Therefore, that's equal to e raised to that linear polynomial. Now, wait a second. E raised to the x plus y is equal to e to the x times e to the y. Therefore, the right-hand side is equal to that expression there, and we can determine that e to the 1.572 is approximately 4.816, and this is times e to the negative 0.235n. So at time t is not, or when n is equal to 0, this is equal to 4.816, and if you want to find out what the count will be approximately after n units of time, then you would just substitute n into this expression and do the calculation. So we can also plot that, and that plot shows us that, yeah, that's probably quite reasonable that that data does indeed come from that exponential decay, from an exponential decay. Now, interestingly enough, we can also find the half-life by solving for what value of n is e to the negative 0.735, or e to the negative 0.235n equals 0.5, or half. So at time n is equal to 0, the quantity is 1. How large does n have to be for this to equal 1/2? Well, we can take the logarithm of both sides, the natural logarithm, and then we can divide both sides by negative 0.235. So therefore, the half-life is the negative logarithm of 0.5 divided by 0.235, and that's almost 3. So if these are being sampled once a year, then the half-life is approximately once every 3 years. That is, after 3 years, the data will be approximately, or quantity will be approximately halved. Now, if the data we were looking at was actually exponentially growing, then the coefficient b would be greater than 0, as opposed to being negative, as we saw in the last example. Also, you could calculate the doubling time by solving e to the bn equals 2 once you've estimated b. Of course, the doubling time is just the negation of the halving time. Now, what do we do about the case where the growth is of the form a times n to the b ln of n, or a times n to the b ln of n raised to the power c? There is a small problem here because we now have logarithms together with polynomials, and yet a logarithm grows slower than any polynomial where the exponent is greater than 0. the logarithm ultimately grows slower than even n to the 0.001. So we could apply the logarithm to the left and right hand sides of each of these expressions. In this case, we now have ln of a plus b times ln of n plus ln of n on the right hand side, but there's no coefficient in front of the ln of n. So in fact, what we would do is we would bring that to the left hand side and then find the best fitting line that passes through that data. Alternatively, here we have a linear combination of three functions, the constant function, ln of n, and ln of n, in which case we would now have a matrix that was some dimension by 3. So we would be fitting we would be finding 3 coefficients. Now, this is really not useful to find out what B and C are, simply because any noise is almost certainly going to swamp out the logarithmic component. But it is potentially useful to confirm that your implementation is indeed, say, for example, n log n. These techniques would, however, be useful if we were testing to see if our algorithm was of the form a times ln of n raised to the power c. In this case, we would plot and match log of the runtimes versus logarithm of a, or an unknown, times 1 plus c times log of n. This is where this technique could actually be used to find the value of c. So you could, for example, look at binary search and confirm that its runtime is big O ln of n. Let's go through an example. Here we have some x values and some y values. Now let's plot these as a sequence of points, and we get this graph here. Now looking at the graph, you may ask yourself, is this growing polynomially or is it growing exponentially? Well, let's find out. Let's plot both a semilog and log-log plot. Starting with the semilog plot, we see this. Now, taking a look at this, it does appear that the points do indeed fall on approximately a straight line. Remember, this data does have noise. If, however, we do a log-log plot, if we look at the image, it doesn't appear to be growing in a straight line. Instead, it seems to be superlinear. Therefore, this suggests that the growth is not polynomial, whereas the image on the left suggests it is exponential growth. All right, we can now find the best fitting exponential curve. First of all, we're going to create the Vandermonde matrix. For fitting a information or a straight line to exponential data, the Vandermonde matrix has a column of 1s and a column of the x values, not the logarithm of the x values. Therefore, the first coefficient will be log of a, and the second coefficient will be b. We can solve this by having the target vector being log of the y values, or the target values, and therefore we get these two results. The first one is result of the actual a, and the second is the multiplier in the exponent. We can raise the first one to e, and we get that result. Therefore, the best fitting exponential is approximately 4.8379 times e to the 0.1558x. We can now plot the data and the corresponding exponential curve. And as you can see, it is actually a reasonable fit to that data. Suppose we have this data instead. Again, let's plot the points. And looking at the result, we can ask ourselves, is this growing polynomially or is it growing exponentially? Let's plot both. Here's our semi-log plot. Now, if we look at the semi-log plot, you'll notice it doesn't really appear to be a straight line. It actually seems to be curving down, so it's concave down. That suggests that it is not exponential and sub-exponential. Therefore, that suggests it's probably logarithmic. So doing a log-log plot, we see that, well, now the data does appear to fall on approximately a straight line. Therefore, we can say with reasonable confidence that this is likely polynomial growth. Now, in reality, you're never actually going to probably have to decide whether or not you're dealing with polynomial or exponential growth. If you're looking at natural phenomena, often you will have exponential behavior, whereas if you are trying to look at the runtime of an algorithm, if it was your intention to write a polynomial time algorithm and it runs exponentially, you have a much more serious problem. But however, let's carry on. Let's try to find the polynomial that best fits the data on the right. We can now find the best fitting polynomial curve. At this point, the van der Waals matrix has a column of 1s for the constant function and a column of the logarithms of the x values, because we're finding the best function that matches log of x versus log of y. We can find the coefficients. Now, the first coefficient is actually log of, or the natural logarithm of the first entry, and so therefore we must actually raise that first entry to the base e. That gives us this value here, and the second entry is the exponent of x. Therefore, the best fitting function that passes through the data is this function here. We can now plot the data and the best fitting polynomial curve. As you can see, this example is a little bit more noisy than the previous example. However, I did actually create this data starting with an exponent or a power of log base 2 of 7, which is closer to 2.8. But again, 2.75 is reasonably close to 2.8. So this is actually, once the noise is added, a reasonable estimate. Following this topic, you now understand that you can use least squares best fitting polynomials to find both polynomial and exponential growth. You know that the data can be transformed into linear data by taking the logarithm of both values for polynomial growth and taking the logarithm of the counts for exponential growth or decay. You understand therefore that on these results, you can use least squares best fitting techniques, and these are going to give us the best estimates of the unknown coefficients. Finally, you know that you can calculate the half-life for exponential decay by solving e to the bn equals 1/2, and the doubling time by solving e to the bn equals 2 if there's exponential growth. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!